So the first thing we want to understand about these voltage-gated sodium channels is that they are voltage sensitive. So they're going to do a different thing at a different voltage, right? That's their nature. So they are voltage sensitive. All right? They're going to be activated at threshold. Activated at threshold. And what was our threshold voltage? Negative 55 millivolts. All right? They're going to be deactivated at positive 30 millivolts. That's sort of the peak of our action potential. The membrane potential doesn't exceed positive 30 throughout the various events of the action potential. That's really important to remember. Now, specifically for sodium's voltage-gated channel, there are two gates on there. Right, so two gates. And that's kind of where the confusion comes in with sodium. There's an activation gate. Okay. This is voltage dependent. Voltage only. Alrighty. And then there is an inactivation gate, right? So on the same channel, two gates. One is an activation gate, one is an inactivation gate. The inactivation gate is voltage and time dependent, right? So voltage and time dependent. Alrighty, so let's actually draw out the three stages of this channel and talk about the different configurations of the gates on the channel, right? And we're going to look at things at rest, which we know to be what voltage? Negative 70, correct, right? Negative 70 millivolts. We know that depolarization happens at negative 55 millivolts. And we know that repolarization starts at positive 30 millivolts, okay? So we'll look at the gates under these three conditions or circumstances. So let's just draw these channel-looking structures. And we want to remind ourselves that these are transmembrane proteins, right? So they're embedded in the membrane here. So think about your phospholipid bilayer occurring across here. This is our ECF. This is the ICF, okay? And we have our channel in the membrane. Now on this channel, at rest, we know that the activation gate is closed, right? But there's a second gate on this channel. It's the inactivation gate, and it's open, okay? It's open. Right, so this kind of represents our inactivation gate. So the activation gate closed, inactivation gate open. And as a result, at rest, at our negative 70 millivolts, this channel is closed, and but it is capable of being opened. Sorry. So the channel is closed, but capable of being open, or capable of opening. Okay, and that's purely because the inactivation gate is open. This is like our second security gate. It's sort of securing things like a backup gate. So if the gate were closed, if the inactivation gate were closed, this channel would be incapable of being opened, but it is. So we could potentially open the sodium channel, right? Let's make a note here. Activation gate open. Inactivation gate, oh, I'm sorry. Activation gate closed. Inactivation gate open. okay? Now, we have a series of graded potentials such that we exceed our negative 55 and we reach threshold. Now we're gonna fire an action potential. So this membrane becomes depolarized, and so we have opening up of those voltage-gated sodium channels, right? And by that we mean that the activation gates are now opened, as well as the inactivation gates. Right, so both gates are open, the channel is open, right? So the channel is open here, and that's because the activation gate is open, and the inactivation gate is also open. Okay, everyone with me so far? So we've depolarized this membrane, we're having that upstroke of the action potential, and that's purely because these channels have opened, sodium is rushing into the cell, and so the membrane potential is slowly approaching the equilibrium potential for sodium, right, which is way positive, positive 60. But we don't actually get to sodium's equilibrium potential, we stop at positive 30. Why? Why do we stop at positive 30? Because these gates are voltage dependent. So at a different voltage, they're going to do a different thing. That's very important to understand. So when we get to our positive 30 millivolts, right, the membrane begins to repolarize. What we have is a timed delayed response of this inactivation gate. So at negative 55 millivolts, there are two signals sent here. One is to close the inactivation gate, and then to open it after 1 millisecond, okay? I hope that makes sense. Let's draw that out. So we have our repolarization happening here. Now our sodium activation gates are still open, right? These gates are still open, but the inactivation gate has closed. Okay? And so now the channel is closed, and incapable of opening. All right, and that is because the activation gate is open, but that second gate is closed. So this channel is essentially closed. And even if we did depolarize the membrane, this channel would not be capable of opening, right? Because that inactivation gate is closed. And this membrane would not be possible. It's not possible to open this channel again until the membrane gets back to rest. So from positive 30 all the way back down, we're actually going to overshoot that negative 70. We're going to go a little bit lower than that as we sort of approach potassium's equilibrium potential. And then we actually reflexively come back up to our baseline. And at that point, will this channel go back to its original configuration because the membrane is now returned to its rest, which is negative 70. All right, so you want to make a note here that there's a 1 second delay here, a 1 millisecond delay for this inactivation gate response. So essentially, two things happen with the activation gate during depolarization. All right, it's going to open, right? It's going to open, but there's a 1 millisecond delay where it's also going to close. So it'll open at our threshold, and then there's a 1 millisecond time delayed response, right? The signal is also sent during depolarization, but after 1 millisecond, it'll close. Okay, and that is to ensure that this is a timed event in the action potential. Okay. All right, any questions on these channels and the gates? I'll point out here, we're going to speak about this later on, but I'll point out here, this phase is in sync with what's called the absolute refractory period. right? The absolute refractory period. And there's that period right after an action potential where we cannot fire another action potential. Even if we get graded potentials, even if we depolarize the membrane, this channel is incapable of being open, so therefore we physically cannot fire another action potential. And that happens, and that's called the absolute refractory period. We're going to talk about what that is later on, but just bear it in mind in context to the gates, right?